I'm Sasi, Research Assistant at the National University of Singapore. Today, I'll be presenting our tool, ML Privacy Meter, designed and developed at the NUS Data Privacy and Trustworthy Machine Learning Lab. Since the past few years, there has been a huge speculation and discussion around the privacy risks of AI. Several concerns were raised about protecting personal data in AI systems. In fact, as per Article 35 of GDPR, it is mandatory to perform a data protection impact assessment (DPIA) if a data processing involves innovative technologies such as machine learning. The key steps in performing a DPIA are to assess the potential threats to data and identify possible risk mitigation measures. Traditionally, when performing DPIA, organizations focused on illegitimate access to data, say through security breaches. But when we are using a machine learning model in the inference phase, we do not rely on the training data to make any predictions. Hence, at a first glance, it might seem like the data is safe because we are not even touching it to make the predictions. But machine learning models pose a subtle threat to the data by indirectly revealing about it through the model's predictions and parameters. Past work has shown that it is possible to infer about the training data just by observing the predictions of a machine learning model. In a membership inference attack, the attacker infers if a particular record was present in the training set. These attacks were tested against machine learning as a service platforms offered by both Google and Amazon, and they achieved a significantly high accuracy. Membership inference attacks can be a threat on its own when mounted against models trained on sensitive data, say medical records containing diseases such as HIV, which might carry social stigma if found out. In general, membership inference attacks can be seen as a measure of information leakage from the model, and the more successful an attacker is in performing membership inference against a model, larger is the information leakage from the model about its training set. Why do these inference attacks work? Machine learning models tend to behave differently on members, that is records that are present in the training set, and non-members, that is records that are not present in the training set. An attacker with some background knowledge can learn to distinguish this behavior and infer if a particular record was present in the training set. In case of neural networks, if the entire model is revealed, the parameters and the gradients with respect to the parameters, especially in the final layers, reveal a lot of information about the training set. This brings in new challenges for data protection laws when designing AI regulatory frameworks. In fact, the European Commission, which is the executive branch of the EU, calls for adequate protection of privacy and personal data in using AI and build systems that are resistant to attacks. Similarly, the White House memo on regulating AI applications emphasizes on data protection throughout the operation of an AI system, which includes the inference phase. Recent reports published by the ICO UK on auditing AI and NIST US on securing AI applications highlight the threat to training data from machine learning models, and they specifically mention membership inference as a potential confidentiality violation and privacy threat to training data. As per the auditing framework of ICO, it is mandatory for organizations to ensure that models do not expose personal data when deployed. The internal teams at ICO will be using this framework to assess if an organization is compliant with data protection regulation laws. Hence, organizations should account for and assess the privacy risk to training data from machine learning models. But how do we measure this indirect leakage about data from complex machine learning models? Our tool, ML Privacy Meter, generates risk reports for the training data from machine learning models. It produces risk scores for all the records in the training set. These scores can be useful in identifying the fraction of records that are under high risk of being revealed to the model. Whether it is just providing query access to a model or revealing the entire model, ML Privacy Meter can readily estimate the privacy risk to training data. How does ML Privacy Meter work? ML Privacy Meter works by implementing membership inference attacks against machine learning models and is based on the state-of-the-art attack techniques. It simulates attackers with various capabilities and different levels of background knowledge about the training data. The attack techniques are from our recent papers and are based on the foundational works that measure information leakage from the predictions and parameters of a machine learning model. Given any data record, ML Privacy Meter automatically generates risk scores from each of our simulated attack. These scores represent the particular attacker's belief that the record was present in the training set. Larger the separation between distribution of these scores for members and non-members, the easier it is to perform membership inference attack. Success of the attacker can be measured by an ROC curve, which represents the trade-off between true positive and false positive rates. False positives corresponds to identifying records that are not present in the training set as members, and true positive refers to identifying the records that are present in the dataset as members. A trivial strategy, such as random guess, can achieve equal rates of true positive and false positive rates. ML Privacy Meter automatically plots the ROC curves that are achieved by our simulated attackers. The area under these curves represents the success of the attack, and higher the area under the curve, larger is the risk to training data. These numbers not only quantify the success of a membership inference attack, they can also be seen as a measure of information leakage from the model. Such quantification of risk from machine learning models can be very useful in performing a data protection impact assessment, DPIA. The key aim of performing a DPIA is to analyze, identify, and minimize the potential threats to data. ML Privacy Meter can help practitioners in all these three steps of performing a DPIA. It generates detailed risk reports for the training data, which help in identifying the records that are under high risk. It allows for comparison of risk across records from different classes in the training set. It also allows for comparing the additional risk due to revealing the entire model with the risk due to providing only a query access to the model. Once these risk reports are obtained, practitioners can learn to identify the source of this information leakage and choose possible mitigation measures. For example, if it's due to overfitting to the training data, they can fine-tune their regularization techniques, or if it's due to overfitting because of insufficient data from certain classes, they can add the appropriate data and retrain their models. Or they might even choose to learn with a proper privacy protection in place. For example, differential privacy, which is a standard notion of statistical privacy. A learning algorithm is said to satisfy differential privacy if the models that are obtained by training on a dataset that differs by only one record are indistinguishable to an external attacker. The level of indistinguishability is controlled by a privacy parameter epsilon. Open source tools such as OpenDP and TensorFlow allow for training models with differential privacy guarantees. But when using these tools, selecting epsilon is a highly non-trivial task. Smaller values of epsilon ensure that we get better privacy guarantees, but it also means getting a less accurate model. Epsilon is just a worst case upper bound on the privacy risk, but it might not accurately capture the practical privacy risk for this particular dataset that we are using. So how do we select a decent value of epsilon? ML Privacy Meter can help in selecting the value of epsilon by quantifying the practical risk at different values of epsilon. Depending on the risk tolerance level and utility expectation level, practitioners can choose the corresponding value of epsilon after quantifying the risk using ML Privacy Meter. Instead of relying on the guarantees by epsilon, using this method ensures that they deploy models with way better accuracy. Hence, by providing more utility, we expect ML Privacy Meter to boost the use of privacy enhancing techniques. The tool is publicly available at the GitHub link shown. Please do check it out, and we are welcome to contributions from the open source community. So please feel free to contact us with questions and suggestions to improve the tool. Thank you.